This is the first video for BC Calculus on logistic growth and partial fraction decomposition, section 6.5 in your textbook. So first thing I want to talk about really quickly is what the concept of logistic growth is. So a logistic growth model is going to be a model that starts off looking exponential, where it may be relatively flat at the beginning and then all of a sudden it just increases very rapidly. And then the graph is going to change concavity to where it actually then begins to approach what we usually consider to be a maximum sustainable population, because a lot of these logistic growth models are going to be population models. So it goes from something that initially looks like an exponential function like this to something that actually ends up looking like a logarithmic function and has a horizontal asymptote up there at the value that is the maximum sustainable population. So, like I said, this is very often a model for real-world problems than a basic exponential function. For example, people like to think about population in a specific area as growing exponentially because you start with 2 people living there and next thing you know you have 8 million people living there. However, you also have like a maximum capacity of that space to where the population, even though it'll reach a really large amount, it'll start to level off at a certain point. And so that leveling off is the maximum sustainable population. So before we get to the differential equation for that, though, we need to learn a little bit of algebra as far as how we would then solve those differential equations. And so that's where we're going to get into partial fraction decomposition. So partial fraction decomposition is going to come from when you're trying to integrate a rational function. It would be some polynomial p of x divided by some polynomial q of x, where the degree of the numerator is less than the degree of the denominator. So that's a rational function. And it would be one in the sense that the q of x could not be factored to eliminate the p of x, or p of x is not some form of the derivative of q of x to where you could use u substitution. So before we actually even do any integration, I want to review some algebra with you. So I've got this function f of x equals x minus 13 over 2x squared minus 7x plus 3. And I want to rewrite that function as a sum of rational functions with linear denominators. So essentially, I want to break that rational function or that fraction up into 2 separate fractions or more that when I add them together with common denominators and that sort of thing, I would end up with x minus 13 over 2x squared minus 7x plus 3. So essentially what I'm saying is I would get this answer by adding together separate fractions, usually with linear factors for their denominator, of the 2x squared minus 7x plus 3. So the first thing you would need to do is you would need to factor 2x squared minus 7x plus 3. So that would factor into, and I just did guess and check method. You use whatever method you want for factoring as long as you do it correctly. It would factor into 2x minus 1 and x minus 3. So that means that if initially I had some fraction with 2x minus 1 in the denominator and another fraction with x minus 3 in the denominator, through the process of finding common denominators, the denominator would end up being 2x minus 1 times x minus 3, which is where that 2x squared minus 7x plus 3 comes from. The only question is, what were the numerators in these individual fractions to where I would end up with x minus 13? So I essentially have an equation now that I'm trying to solve for A and for B. So here's the process that I would go through to do that. Well, the first thing that I'm going to do is I'm going to focus only on the numerators. Like I know what the denominators are right now. To get rid of the denominators, I would multiply the entire equation by the common factors of the denominators, 2x minus 1 and x minus 3. In doing that, the first fraction, the entire denominator would be wiped out to where I just have x minus 13. in the a over 2x minus 1, the 2x minus 1s would cancel, and then I would have a times x minus 3. And then with the b, the x minus 3s would cancel, and I would have b times 2x minus 1. So now at least I'm not solving a fraction or a rational equation. I'm just solving a regular multi-step equation. So if I distribute my a and my b, I get x minus 13 equals ax minus 3a plus 2bx minus b. Okay, so again, I've got this one equation though that has both a's and b's in it, and x's. But if you focus on the individual parts, like if I focus on just the x terms, what that tells me is that in order to get one x over here on the left, the ax and the 2bx would have to combine in some way to give me that 1x. Or, now that all the terms have an x in them, 1 equals a plus 2b. As long as a plus 2b gives me a value of 1, then I would get that x for the x minus 13. Now, let me change my color. We'll do purple. I can do the same thing with the constants. To get a negative 13, I would have a negative 3a and a minus b. So now, between the purple equation and that last red equation, I have a system of equations. I have 1 equals a plus 2b, and I have negative 13 equals negative 3a minus b. So a system of equations, going back and doing some more algebra, I could do substitution, I could do elimination, you could do matrices, you could solve by graphing, but we're probably going to stick to either substitution or elimination. I think I'm going to try elimination, and I'm going to take this guy and multiply everything by 3. If I do that, I'm going to get 3 equals 3a plus 6b. So then when I add him to my purple equation, I'll get negative 10 equals, and my a's eliminate. And I get 5b. So that would tell me that b would be negative 2. And so then if I could then plug that negative 2 into either the red equation or the purple equation. So if I substituted into the red equation, for example, I would have 1 equals a plus 2 times negative 2. 1 equals a minus 4. So a is equal to 5. So now that I know what a and b are, I can actually go and write back at the beginning, instead of a over 2x minus 1 and b over x minus 3, I can put a 5 here and a negative 2 here. So this is the sum of the individual linear rational functions that would add together to give me x minus 13 over 2x squared minus 7x plus 3. So that takes us to the next example. What if I wanted to integrate x minus 13 over 2x squared minus 7x plus 3? Well, that integral is the same as integrating 5 over 2x minus 1 plus the integral of negative 2 over x minus 3. So the whole reason we split that complicated fraction up into partial fractions is because now integrating those linear denominators can be done very easily with u substitution and with logarithms. So I'm going to do each one individually, and then I will worry about adding them together. So for this guy, your u is going to be your denominator. So then du would be 2 dx, but I don't have a 2 in my integral, so it would be 1/2 du equals dx. So that makes my integral, I still have the 5 in there, and I have the 1/2 from my du, but instead of the 2x minus 1 in the denominator, I've got a u in the denominator. So The two coefficients give me a 5/2, and then 1 over u integrates back to natural log of the absolute value. Don't forget that absolute value. That's important on these problems. And so then we would substitute our u back in. So this guy integrates to 5/2 natural log of 2x minus 1. All right, now I'm going to do the other guy in red. And you're going to do him the exact same way. U is going to be your denominator. So du is dx. So that makes this integral. The -2 is still there, times 1 over u du. So it becomes -2 natural log of the absolute value of u, or -2 natural log of the absolute value of x minus 3. Now, if we go back to the beginning of the problem, these two integrals were being added together. So our overall integral of x minus 13 over 2x squared minus 7x plus 3 is the sum of these two answers. So 5/2 natural log of the absolute value of 2x minus 1 minus 2 times the natural log of the absolute value of x minus 3, and then the plus c on the end. So if this was a multiple choice question, or a free response question, you could be done. Or if it was a short answer on a quiz, you could be done. If this was multiple choice though, they're going to use some properties of logarithms to simplify this even farther. Typically these partial fraction problems as multiple choices have just one logarithm for the final answer. So we need to think about how we could combine these two logs into one log. Now you may see the subtraction between them and think, oh, I can just divide. And you're partially correct. We can divide as long as the coefficients in front of them are the same. But they're not. One of them has a 5/2 and one of them has a 2. So what we would want to actually do first is we would want to write these with, remember we can put the coefficients as the exponents, like that. Then they do technically have the same coefficients in front of them now because the coefficients are both 1s. So we can combine them into a single logarithm with 2x minus 1 to the 5/2 over x minus 3 squared, and then the plus c at the end. So that would be what the multiple choice answer would look like. So that's going to wrap up our first video. So I'm going to make a few more videos going over the rest of the examples for you.